Uh, Good morning, no, that's wrong. Good afternoon, so we're already past 12. My name is Heiko Lehmann. I'm here from T-Labs, from Deutsche Telekom laboratories. And I would like to talk about the digital twin for disaggregate networks. Jean-Pierre already gave away that I'm by training a physicist, yeah, and I was very I like to read that he's the Einstein professor, because Einstein, you can imagine, is one of my patron saints. And Einstein said, make it as simple as possible, but not simpler. And this is something I quote very often. And I think it might very well be quoted in the context of digital twins. Yeah, so digital twins, of course, is a marketing term, is nothing scientifically rigid. Let's spend a couple of minutes to dwell on that. Basically, I said that, yeah, so this is a trend in science which started, I believe, in the 70s of last century, yeah, that was the term chaos theory. You might have read that, yeah, you could call that, Slavomir, is it theory of nonlinear differential equations? That would be the accurate term, but if you call it chaos theory, which the people then did, you have a higher chance of it being picked up by journalists and the media and the general public, yeah, because it sounds much nicer. I think it's the same as digital twin, yeah? But what it comes down to in the end, it's a mapping plus some dynamic modeling, and that's the problem, and that is what we should think about a bit in the context of disaggregate networks in the next couple of minutes. So as people nowadays always do, let's start with Wikipedia. Yeah? So there is, as I said, there is no definition, but they tried it. So the digital twin, they say, is a virtual representation of something of the real world. But then the problems already start. Yeah? It's a virtual representation of what? I have an example here, which is also, Matthias told me in every talk of digital twins is always this turbine. Yeah? And you can look at it and ask, what is the virtual representation of this thing for? And when you're planning a factory, when you're an architect and you need to plan the floor layout and possibly logistics or whatever, then it would be enough to model the shape. Yeah, to have a 3D model of what that thing looks like. If you're interested how the thing behaves dynamically, then of course you have to add more information to your virtual representation, which is mass, density, materials. You have to worry about the joints. Is it welding? Is it nuts and bolts? Because that will behave differently in a dynamical context, and so forth. You already see what I'm getting at, yeah? So you can ask ever more detailed questions. In the end, you can ask about material fatigue, what's happening in the long term. You can ask about inhomogeneities, which might, in the long run of the dynamical operation of this thing, will lead to other phenomena. So it's basically endless. And in the end, you would need to model every molecule of that thing, and then it's senseless, because it's not the representation, but the thing itself. Yeah? So this is the first conclusion. If we need to draw, a true twinning is an illusion. And the best we can do is that we devise a set of useful tools, which should be scalable or modular. We will think about that more in the following minutes. And you would first need to be sure about the questions you ask. When you're clear about the questions you ask of that model, then you can devise the tools. And you must always be sure about its limits and boundaries. Yeah? And this is now coming from the turbine, from this machinery world to our world, to the world of telco networks. This slide actually is stolen from Daniel, who's sitting over there. He is doing all the work. So the scientific collaborators are in the room here. And what you can see here is the modularized picture of the NS3 modeling of networks. NS3, yeah, it sounds cryptic. It's network simulation. That's the big open source a modeling system for dynamics in the networks. And this is actually what we are doing in this project. So the project itself is called Open Lab. This lab is called i14y, so it's a bit confusing, yeah, but the government-funded project is called Open Lab, and in that we have a partial project which is called Technological Evolution. It's led by Dr. Kasparik, sitting over there. And in this, the logic of this partial project is whatever the actual lab is doing, you will be led around later on. We are building a complement to that. And why do we do that? Yeah, so the idea of the lab itself is you have a component and you come to the lab and there you have a reference implementation of the future real world ORAN implementation, and you can plug in your component, and if it all works out, then you get a test report and you get a certificate, well, yes, this plays with ORAN. Yeah. But what can they do? The only thing they can do in the lab is they can test conformity with interfaces, with protocols, with specifications, and test really how it works if you plug it in. We thought we need to test more. We need to test the systemic behavior, and that you can never do in a lab. That you can only judge in the real world. If you have realistic load patterns, if you have realistic neighbors, if you have realistic situations possibly of interference, if you have realistic topology input, this is not, can never be achieved in a lab. It can be achieved in field trials, but then you have just one instance and you can test the conformance with this field trial. But if you have a powerful simulation system, then you can fool around with it and you can give it the task, model me in a city, and the next day you can tell it, model me a rural area or something in between. Yeah? So this is what the ambition of our partial project in this bigger project is. So we want to have the capability to test components with respect to their virtual behavior. Systemic behavior. So this is a breakdown of the available NS3 components. As I said, Daniel did this work. And the good thing is it's modularized and we can reuse a lot of things that have been done before. So all what is marked green here, we do not need to worry about. And of course, we need to make adaptations because Open RAN is about disaggregation. And some of the historical modules which you find in this suite of NS3 tools, are not disaggregate, so we have to do that. But, of course, it's a rhetorical question. This is not a full digital twin because we need this other property as well that we capture as well as we can the real world. And this is now not a solution, yeah? So we are not in that stage yet. The project has just begun. I should say that this idea of having a virtual instance of testing X apps, R apps with respect to their systemic efficiency is taking ground. Yeah, we had this idea first, but our friends from Facebook in North America picked it up, and they are working on the same thing. But the good thing about openness is there is no rivalry, and there's no question who's the first. Of course, scientists want to have the first paper out, which is then quoted all the time. Yeah, that's a fine ambition. But for us, our point of view from the industry, it's the big advantage of, for instance, this NS3 thing that it's open, and academic groups all over the world are contributing to it. Stavomir and Martin and Daniel are doing that here from Berlin. In Barcelona, there is a strong group, and apparently, we have to find out what they do, but apparently at Northeastern University in the US also. Yeah, and in a perfect setting that would all contribute to one powerful system in the end. So, as I said, this is the state of our discussion. We haven't built that thing yet. We first need to be clear, very much in the vein of the first slide, to understand which questions should we ask and what kind of answers we hope to get. And the first thing you realize, so this is now the translation of the molecular level versus the shape thing of the turbine, the translation of this divide into networks. Yeah? So these are two ends of a coarse graining spectrum, so to speak. You can ask very detailed questions about how electromagnetic waves are propagated, how they are reflected of surfaces, and as I said before, you get from one level ever finer to the next level. Yeah? So the first thing is to model a building. Nice. Yeah? Then you have reflection pattern. But then you realize, oh, it depends on whether there's a glass pane or whatever the surface of the building is. Yeah? And then possibly you even need to model humidity in the air and things like that. So all this has a bearing on this molecular level of networks, if I may use this mingling of metaphors. So, and of course, if you want to answer this, then you need the appropriate tools which are around. Yeah, so they are getting better. We saw that in the presentation yesterday of Artesio. But possibly you do not want to worry about that. Possibly if you just want to give a label to a component, open RAM component, as I said a couple of minutes ago, then you might be completely ignorant about the electromagnetic waves. You just, Michael Leise, ich rede hier. You just do not worry about the wave propagation. You're interested in aggregate KPIs per component, per cell aggregate KPIs, and then you might have a different simulation system, only looking at the input-output of the components with respect to the interplay of the ORAN disaggregation. So you have to be clear what questions you want to ask, and then you can choose your tools. And if you do it in a wise way, it's not integrated, so that you really can switch off things and have a modular structure of it. The next thing you have to clear about is also very important. Maybe this is also a very basic thing of a digital twin. It might even help for definition. So, because it's a mixture of two, as I said. So one is a high definition photograph, if I may use that analogy. Yeah? So you try to capture the world as well as you can, and in as fine a structure as you can. As we were saying about buildings and surfaces and materials and so forth. But this is only one thing, and you can do that via data. And this is, of course, the power of modern computing technology, that you can get in ever more data. Yeah? But then what you do with it, you want to evolve that in some sense, because you want to ask scenario questions. You want to know what does it evolve to? Yeah? So the thing is, I have a given state at time t0, and I want to know what does the state evolve to in a delta t. And for that, you need a driving force. And that you cannot photograph. Yeah? So that you have to know. That is modeling knowledge. Yeah? I called it equation of motion. And so the digital twin always is a mixture of these two. And you have to play with the coarse graining level of these two. And yeah, so important to have that in mind, and important when you devise what you are getting at. This is a very naked slide, because I only just added it in the light of comments made yesterday by Slavomir. Slavomir said we have a lot of bad models. And he proposed as an alternative if we might learn it, and that is basically true. So an equation of motion we can either know, yeah, as a model, or we can learn it. But both options have their drawbacks. Yeah? A model might be wrong. I've quoted here the gentleman I stayed with at Oxford University. So he was a very famous statistical physicist last century, 60s of last century. Yeah. And he said an exact formula is equivalent to an infinite amount of computing time, which is true. So that's the power of a model. If you have a model, then you do not need to worry where it is applicable. And that's precisely the drawback of the learning. The learning, of course, can be much nearer to the real world because it relies on the data the real world throws at you. But you always have a limited set of data you put into the learning thing. And then if you try to extrapolate from that, you might make errors. And these might be very grievous errors, and then it might be the end of the rope for the learning approach. So this is also not solved yet. Yeah, Slavomir, did I reproduce this correctly? More or less, okay. That will make some comments later on, I suppose. Yeah, so this is about the setting up of the digital twin, and now a couple of motivations for the utility, what we can use it for. And as I said, we want to have this virtual counterpart to the real lab setup, which is being built here. And the basic motivation for that were logical inconsistencies you might run into if you decouple the real world into apps. This is the logic. This is the logic of the iPhone, and the Oran people borrowed it. And if you look into the structure, you have this famous rig, and there the idea is the apps reside side by side. X apps, R apps, doesn't matter in the moment. And each one is dedicated to solve one problem. And of course, you might have situations like this, where the action space these things act upon is the same or is overlapping. But of course, the driving force in the app, the cost functions or whatever the objectives are different. And then you create conflicts. Yeah? We talked about that yesterday also. Of course, there's always a simple way to solve a conflict. You have to just give priority to one application, but that is just on the short term solving a conflict. It's not contributing to a systemic optimization. And this, of course, is what we want to have in the end. That's why I put here the example of the non-real-time rig, because this is where the network efficiency is decided. And this is where you will have R apps for power save and for other global efficiency measures. Yeah. So, and this is what we want to have our digital twin for. And the winning formula, again, is stolen from yesterday's presentation from Boris. He's not here, so it's a co-worker also in our project from TU Berlin. Is a very astute mathematical guy. And the formula is, we take the concrete formulation of the Oran world plus causality modeling. We do not have time to go into that, but this is trying to find a causal structure among these R apps and how they influence one another and how conflicts really are created. And then if I have Daniel and what he's doing with this NS3 stuff and I can evolve that, then I can first try to detect conflicts, second give a measure to them, and at the end of the line really solve conflicts. So this is the basic motivation why we invented this partial project. This slides, Martin, has been shown in the other room, so I don't know who migrated. Yeah, this is the application of this of our concept of digital twin or / simulation system for overall energy optimization of the system, and this is work done by Heinrich Hertz Institute, and it's very powerful in several ways. One way is that it's formulated in a robust way, so you're not trying to hit exactly the time series in a forecast way, which you can never do, but you're trying to forecast an upper bound to it. Yeah? And this is even tunable, so that's a very powerful approach. And it is essentially non-local. Yeah? So the naive approach to power save is you locally look at the threshold, and when you reach it, you switch it off. But this is first, it is unstable because you might introduce oscillations, you switch it off, then something, the network readapts, and you are slightly above the threshold. This could even be a case of self-organized criticality, so that's bad. And this approach of the scientific partners have non-local properties also in it. Also important when you think about power save is that, in contrast to the old world, where the traffic was really, where the energy consumption was really closely tied to where the traffic is happening, we now have a disaggregation of that because of virtualization. So if you take some compute load to some cloud instance, as I try to formulate that down here, then you have two essential parts of how your energy is consumed, and this gives you the task, but also the levers and the degrees of freedom to optimize in another dimension. Yeah. So this is work which is also going on. This is another example where we want to have our simulation system for. I want you to learn this by heart. I shall ask about it in 5 minutes. No, sorry. This is academic work done by our partners from Ben-Gurion University in Israel. It's abstract modeling of attacker capabilities, but of course we need to map that onto a real system, and we need to map that onto real evolution of traffic situations in the system. And this is also where we imagine that our twin comes in. I'm done. Yeah, so this is, I have no time for that. This is a specific adversarial attack scenario. So a security thing, which we again need our twin to harden the system against. And this is the wrap up here again, as Alphonse already did. I quote the sister project, Campus OS. So I don't know how familiar you are with funding, with the funding world. So we here in the Open Lab are funded by the Infrastructure Ministry. And there is a sister project, the Lighthouse project, Campus OS, funded by Robert Habeck and his ministry, having more in mind the product logic of disaggregate networks, and product being modularized campus networks made in Germany, made by Alphonse, among others. Yeah, so do not have time to go through this. So essentially, it's two parts. It's the capture of data and its evolution of these data. And you have to decide upon the granularity which you're interested in, and you have to decide upon the time horizon and the dynamic properties you're interested in. And possibly it will be not just one twin, as the two I had on the beginning slide, but a tool set and a chain which is configurable. Thanks.